right, that'll do it now. So we'll go through the factorial analysis, and then we'll talk about correlation analysis, which you'll be happy to know and probably have already figured out is one of the simpler things that we'll do. So that's pretty exciting. The ANOVA, I sent you all this already, so you already have all of this. So when SPSS output tells you that the significance is 0.000, you'll report P is less than 0.001 because that's the smallest we can know from that number. Don't forget to italicize the P. And I made comments on some of your papers just about writing the results in text, especially the descriptive information, and just think about how to put that in a more sort of text format rather than broken up into parentheses. Like think about how it would read as a reader. So this blog has a little bit of information about that. Never start a sentence with a number in numerals. And make sure your font is consistent throughout. I think it's like copying and pasting from different documents and probably different documents of mine that are in different fonts. So just make sure that's consistent. And just a small note that the sample that you all looked at for that analysis had only partnered people in it. So some people wrote something like in the full sample. So just make sure you note that it's in the full sample of people who were partnered. So just some detail about the sample itself. Any questions about the ANOVA? The one-way ANOVA?
I don't think so. The feedback was pretty straightforward.
Cool. So I put this on the slide, and I don't mean for this to be an exhaustive checklist. Certainly still look at the rubric, still look at all the templates and the assignment itself. But I put this up here as a little bit of a checklist for you to think about what pieces you have in each of the sections for the weekly assignments anyway. So just make sure you're putting in obviously what you chose and your rationale for that. And don't forget to talk about the assumptions of the analysis. You don't have to go into a ton of detail. You can just say something like the data met the assumptions of the analysis, which were X, Y, and Z. And you don't have to spend a ton of time on that. For the results, putting in the descriptives, making sure somewhere in there you get the sample size and any group sample sizes in there. And then obviously the results. And just make sure you're specific about the directions and the comparisons. I made that comment in several of the ANOVAs. Some people wrote like, these groups were significantly different from one another, but then you have to go back and look at the earlier descriptives to figure out which direction those differences were. So just make sure you're saying that as you talk about the results. And don't forget the effect size. And then for the discussion, I feel like sometimes it's even more helpful to have a checklist of sorts for the discussion. There's some checklists in some of your textbooks as well, but this is one for the weekly assignment in particular. Summarizing the results in plain language, doing some interpretation. So why do you think you're seeing that particular result in that direction? Talking about the implications for practice and research. And then suggestions for future research that maybe would help us better understand our finding or answer another sort of subsequent question to help us inform how we would apply those findings. And I put these asterisks here because these are each of the sections that I think benefit from any literature. And you don't have to. I'm not going to take points off for not citing in the discussion section, but if you have something and you're saying maybe it's because, and you happen to know something off the top of your head, or you can do a quick Google Scholar search to support that, awesome. But in a sort of real discussion section, I'm putting air quotes around real, in sort of like a full discussion section, that would be a place where you would support each of those pieces with existing literature. So a little bit of a checklist, which will hopefully help you as you move through the rest of the weekly assignments. So we'll talk about the factorial ANOVA from last time. These are the findings that I got from the I think I just did one data set this time. Yeah, so just that same data set this time. So were there significant main effects?
Yes.
Yes. And was there a significant interaction?
No.
Yep, exactly. Somebody has not on mute. Well, that sounded like a merry-go-round or something.
It's probably me. I'm sitting in a lounge with my headphones on and someone is singing and playing piano behind me.
Oh yeah,
Sorry.
that's totally it.
That's it.
We started when class started, so yay.
Funny. All right, so yeah, there is no significant interaction, and we know that over here, but there are significant main effects. And if we look at the estimated marginal means, the plot that they give us, the SPSS gives us, we can kind of see where those differences are a little bit. And some of you I know went ahead and ran t-tests for each of the groups separately. And probably when you did, you noticed that in fact, the t-test between men and women among white folks is a significant difference, but the t-test between men and women among people of color is not significant, which is sometimes what we find in interactions. I think we're not seeing a significant interaction because this distance is not significantly different than this distance. Do you see my mouse when I move that, right?
Yes.
Okay, good. I was like, am I just, yeah. All right. So that's why I think why we're not seeing a significant interaction, but you can definitely see the main effects here. So this is the men in the sample, and we can see that for both white men and men of color, they are higher than the women in the sample on their means. And we see around people of color this main effect of race and ethnicity, whereas people of color are higher in body appreciation than white folks are. So those two main effects working side by side with one another, but not interacting. Any questions about the interpretation or about interactions more generally?
Dr. Wells, I have a question about the table.
Yeah.
So clearly I just turned in my assignment like 10 minutes ago.
It's fine. I assume most people did.
But I wanted to know in the table, on the top number, I don't have my assignment open, but I think it's like the total or the full sample.
The full model, yeah.
Full model.
Yep.
Where do we get that number from?
Yeah, so that's this corrected model on
Okay,
this
good.
top row right there.
Okay, because I searched through my book and I was having a hard time finding it.
Yeah.
So I just went with that one.
Yep, awesome. That's the right one.
Okay. Thank you.
Of course.
So I also have a question.
Yeah.
So you said that one of the students did like a t-test, and I'm pretty sure I know like whom you're talking about, but I can't remember exactly what she did. Are we going to go over that at all? Because it seems as though that was pretty important.
Yeah, I can actually show that to you. So in cases when we do find a significant interaction and we have to go in and do a little digging to figure out where it is, essentially what we would do is split the file and run two different t-tests. So if we were to find an interaction here, such that, for example, let's say that these white women over here had really, really high body appreciation, but women of color had really low body appreciation. And for men, it was about the same, whether you were white or a man of color. So that would be an interaction, and we'd want to go in and do some t-tests to figure out where those differences are. And essentially what we would do is split the file according to one of our variables. So we could say, let's split our whole file according to race. And I can actually, maybe what I'll do is pop over to that data set and show you that. So in data, you can go to split file. And so you can take this race variable here and either compare groups or organize output by groups, either one. and then hit OK. And nothing changes in the data set. It's essentially just you're telling SPSS that any analysis that I run after this, do it separately for the people that I've coded white and the people that I've coded people of color. And then you can go over here to compare means and do an independent samples t-test just like you've done before. And you would put the other variable in as the grouping variable. So we split people on race and ethnicity. So now we could take this gender variable and put that in. And I think gender, is that 1, 2 or 0, 1? Thank you.
I want to say 1, 2.
I think 2. We'll go with that and see what happens. And then we'll put that same outcome score in there, that body appreciation score. And then we can just hit OK. And then essentially what that does, it's running it separately for the people who are missing on race as well, but we'll just ignore those folks. And essentially what this is doing is running a t-test for only the white people in the sample, comparing men and women, running another whole separate t-test for the people of color in the sample, comparing men and women. And so when you look up here, you get those same 4 cells that you get when you run that ANOVA. So you get the people who are white and identify as women, the people who are white and identify as men, people of color identify as women, and people of color who identify as men. And you can look at those means on each of those scales. And for white people, we see that there actually is a significant difference between women and men. So that p-value is significant. Whereas for people of color, there is not a significant difference between women and men. But again, the distance between these two and these two is both probably not that large of a distance, a size of their difference, I mean, and it's also in the same direction. So in both cases, we see that men score higher than women. Same here, men score higher than women. And so we don't see an interaction because what we would need to see for an interaction is that these would be flipped. So in one group, it would be higher for women. In the other group, it would be higher for men, or vice versa if we flip that around. Does that make a little bit more sense in thinking about how to do those post hoc tests?
Yes, we want to do a t-test and get more specific information. We just go to data and then go to split, right?
Yeah, exactly. And just make sure you then run your t-test on the opposite variable. People will sometimes go in and say like, all right, I split the file on race, and then now I can do an independent samples t-test and put that race variable in there, which I think is 0, 1 on this one. That's how I've coded it. And then SPSS will say, I freaked out. I don't know what to do because you're putting that same variable in as both a grouping variable and as a split variable. So we're just going to stop. So that's a common mistake. And then people are like, oh no, I don't know if I broke it. And then once you're done doing whatever analysis you're doing, you can just come back under split file and then unsplit it. So don't create those groups. And then,
all right, cool.
Yeah. Any other questions about the factorial ANOVA? All right. On to correlation. Correlation I find to be one of the easiest of all the analyses. I always find it a little weird that in stats, a lot of stats books put it a little later, and you'll notice your stats book puts it both early and late, which I also find kind of a funny thing. But there's sort of 2 separate chapters on that. The basics of correlation are just shifting our focus a little bit. So we have been doing differences between groups, and now we're going to look at relationships between variables. So correlation essentially refers to the extent that one variable is related to another variable. So the 3 things that a correlation analysis will tell you are the statistical significance of the association of the correlation, the direction of that correlation, so whether it's negative or positive, and the magnitude of the association. And we can get that both in the correlation statistic itself, the R, and in the effect size, which is the R squared. And so you probably have seen these Venn diagram overlaps a whole bunch before. Essentially what this is showing us is the overlapping variance. And so if we think of each of these essentially like a histogram, where we've been looking at the normal curve, we can say that like the lines are here, this is the whole distribution of that. Same thing here, and we're looking at how the variance, how the distributions essentially overlap and how their variance is shared or patterned together in some way. And some people find those Venn diagrams to be really helpful in thinking about what that correlation is doing. So we ask lots of research questions with correlations. Are SAT scores associated with college GPA? Is there an association between sexual satisfaction and relationship satisfaction? Is self-esteem associated with contraceptive self-efficacy? Is depression associated with sexual satisfaction? Tons of questions like this. And we'll talk mostly in this lecture about Pearson's product moment correlations, but there are a few other kinds of correlations that I'll go through a little bit towards the end of tonight. But once you understand the basics of the Pearson's product moment correlation, you'll be able to apply that to all the other kinds of correlations. So basic logic, again, this indicates the association between two continuous variables. The Pearson's correlation does anyway. When we get to the other kinds, you'll see some variation according to different kinds of variables. And so again, it tells us the statistical significance, the strength of the association, and the direction of the association. And so we're essentially looking to see if two variables are moving in the same direction. And again, we're thinking about the variance in those variables. And we've talked about this before, but a negative correlation indicates that as one variable increases, the other one is decreasing. And a positive correlation means that as one variable increases, the other one also increases. And correlation values range from -1 to +1. We've covered some of this because so many of the other analyses ask us to think about correlation a little bit. So we've kind of filled in a lot of this correlation knowledge as we've gone a bit. So these correlation values range from -1 to +1. And the closer towards 1 it is, the stronger it is. We also calculate the R squared, which we can interpret in language and in the way that we think about it as the amount of variability of one variable that can be explained by the other variable. And when we say explained, again, you hear a million times, correlation is not causation. So what we're saying is that the variability in one variable can be explained by the variability in another variable. And so we can use those same Cohen's effect size evaluations that we talked about early in the semester to evaluate the R squared effect sizes. And we'll look at a couple of examples of that. So pretty similar assumptions as we've seen in other analyses. This is a bit of a new one in that we don't want a whole lot of outliers or outliers that are potentially really influential. So outliers that are really far out there or really high and potentially having a huge influence on our data. Same as in other analyses, our parametric analyses anyway, we want normal distributions. Linear relationships between the variables, and I'll talk a little bit about what that looks like and how we evaluate that. And then homoscedasticity. And this is the same assumption we've been talking about in t-test and ANOVA analyses, where we're looking at homogeneity of variance. And essentially what this is looking at is to see if there is equal variance of one of the variables at all levels of the other variables. So the variance are essentially, in some ways, the range in Y scores is the same at each level of X scores. And I'll show you a couple of pictures, which I think are easier to visualize that. So we do scatter plots to try and understand both whether or not the relationship between two variables is linear and to look at homoscedasticity. So these scatter plots give us a sense of the association between two continuous variables. And so much like all graphs, there's an x-axis and a y-axis. And each dot on the scatter plot is a case where you have somebody's score on x mapped onto where their score on y is. And so the dot is placed at the intersection of x and y. So each dot is essentially a case or a person for most of our research. So if you say, come over here, this person's score is a 65 on the x variable and a 28 or whatever on the y variable. Same thing over here. This is height and weight. And so you can see where somebody is on this height, so 180-ish centimeters. And for all the people who are 180 centimeters, here's where they lay out on the weight variable. And so when we're looking at homoscedasticity, essentially what we're looking at is the variance in y, in whatever this variable is, at each level of x. And so I think this picture is the one that's in your slides, and I just added this one a little bit ago because I think it's a bit more clear. Homoscedasticity essentially means that at each level here, we see about the same variance. So things aren't getting a whole lot wider, and so our variance is much larger over here at this end of x, and it's much tighter down here. So we see kind of a fanned out kind of effect going on. And we can see that look in both directions, right? So it's less variance or less range over here at the far end of x and a lot more over here at the low end of x. This can go in both directions as well. So we have a lot of variance at the low end, a lot of variance at the high end, and a lot of consistency here in the middle. So essentially what we're looking for is kind of no discernible pattern. So we see that people are all across the board here at each level of the x variable. So we'll look at a couple of examples and think about how to look at that and how to evaluate that. Any questions before I jump into linearity?
So far, so good.
All right. All right, so then the other thing we're looking at on scatter plots is whether or not the relationship between two variables is linear. And what we mean by this is that as one variable increases, the other one either decreases or increases in a linear fashion. So it keeps going in the same direction. In nonlinear relationships, we might see U-shapes or upside down U-shapes. Maybe, for example, at very low levels of X, people tend to be higher on Y. And as you come down on X, people tend to be lower. But then if you come over here high on X, people tend to be high on Y again. So that's a nonlinear relationship, and the Pearson's product moment correlation is not good for that. There are other kinds of analyses that we would use for special cases like that. So when we look at the scatter plots, we can also add the regression line to them, which will become even more relevant next week. So the regression line is a single straight line that essentially tries to come as close as possible to all the data points. And it tells us both the strength and the direction of the association between the two variables. And the greater the extent to which the dots are clustered along that line, that's a pretty good indication that the association between those two variables is probably a stronger association. So this is an example of how much time you spend studying in minutes and quiz grades. So we see that the more time studying, the higher the grade is. And so what this line does is tries to give an estimate, and this estimate is done using this formula. So it's essentially saying for every value of X, we can try and figure out what Y is by adding both the slope and the intercept. I'll talk a little bit more about those now and then also more next week. So in this regression line formula, you probably remember this from like 6th grade algebra at some point. I certainly remember arguing with my math teacher and saying something to the effect of, I will never use this in my whole life. Here I am. So clearly I was wrong and also kind of an asshole. So the regression line formula then is, y is this outcome variable that we're trying to generally predict and figure out what it is. A is the intercept, or the point at which that regression line crosses the y-axis, that vertical axis. B, or beta, as we'll start calling it, particularly next week when we go into regression, is the slope of the regression line. So the amount of change that's produced in y by a unit of change in x. I'll show you a picture of that in a second because I think that's really hard to understand. And then x is the score on that independent variable. So essentially what that equation does is tries to find the best fitting line, the one that has the least amount of error or residual. And we want to try and minimize the distances between the values that we would predict using this equation and the actual values that we see when we conduct the research. So again,
quick question.
Yeah,
Sorry.
yeah, of course.
So then, is that formula the same as y equals mx plus b?
Exactly. Yep. Yep, same thing. And you'll see it sometimes written a few different ways. So sometimes people will move those around, but the premise is still the same thing, that we're trying to make a prediction about y using what we know about the slope of the association between these two. So how steep this is essentially, and the intercept, which is where it essentially crosses that line. So, so that gives us a little bit of information about what we know that relationship to look like, and then we can take that information and try and make predictions based on it. So that's sort of all the foundation for regression, linear regression, which we'll talk about next week. But yeah, y equals mx plus b is probably how you have heard it in algebra. So yeah, we were all wrong about not needing that. So any questions before I jump into the nuts and bolts a bit more?
No.
All right.
Yes.
So same 4-step process. We're talking about the null and alternative hypotheses, making sure we meet those basic assumptions that we talked about, calculating the test statistic, and then make a decision and interpret the results. So same as we've been doing. So if we're doing a Pearson's correlation, that we're making sure that the level of measurement is continuous on both the independent and dependent variables. We'll talk at the end about different kinds of correlations that have different assumptions or intentions. We want to try and have very few or non-influential outliers. Make sure we're normally distributed on both variables or pretty close to it. The relationship between the two variables is linear, and that we have homogeneity of variance. And then you just calculate it. So luckily, again, we don't have to do anything. We can do that all in SPSS, although this is a fairly simple formula as far as formulas go. So
are you saying that makes sense to you right there?
I didn't say it makes sense. I said it's a much simpler formula.
Uh-huh.
There are fewer things going on.
I think we need to define the construct of simple.
I was defining it relative to like thinking about factorial ANOVA.
Okay.
Yeah. So this is a formula that we could try and figure out. Essentially, what this is doing is thinking about this regression line. And thinking about what the values are and what we're predicting the values to be, and doing some summarizing of that. But all we have to do, thankfully, is use SPSS. And we need to look again at the p-value to figure out statistical significance. We want to look at the strength of the association, And then think about, again, does this really, even if it's significant, does it actually matter? So going into an example from our data set, I looked at whether there is an association between experiencing each of the types of jealousy. I think I just went with cognitive jealousy in this example, and evoking jealousy from one's partner. So that evoking jealousy scale is measuring your agreement with different statements about things that you might do to try and make your partner jealous. And then again, the cognitive jealousy scale is kind of your suspicion of your partner in a lot of ways. So the null hypothesis would be that there is not an association between experiencing and evoking jealousy. The directional hypothesis would be that there's a positive association. A non-directional hypothesis would just be that there is some association there. So for our data, we have two continuous variables. We have a linear relationship, which I'll show you in just a second on the next slide. And we'll check for homogeneity of variance. And then we'll look at the distribution on both variables. Cognitive jealousy we've looked at before. We said it's pretty fine, even though there's a little bit of skew on that, but it's not terrible, and we have a pretty big sample. This is the evoking jealousy scale. So as you can see, we do have some skew over here, but if we look at the skew statistics, we generally want that to be under 2. So we're right up on the edge of that, but we have 1,500 people who have evoking jealousy scores. So again, we're underneath the skewness sort of cutoff. We're underneath the kurtosis cutoff. And so because we have a pretty big sample here, we're not going to worry so much about it. Again, we see that this mode is a little off down here because we have so many people who, on the bright side of things, are super low on trying to do things to make their partners jealous. So while that's not fantastic news from a distribution perspective, from a humanity perspective, relationship perspective, it's probably a good thing, right? So we're going to go ahead and say that the normal distribution assumptions are met for both of those variables. And then we have the scatter plot here, and I've put the regression line on there, and I'll go into SPSS and show you how to do all of this as well. And so when we're looking at linearity, if we look at this regression line over here, it does look like we can see some level of linearity in the relationship, such that as these scores get higher, these scores tend to get a little bit higher as well. We put the regression line on there, and essentially what this is saying is if we take any of the scores on X and multiply it by 1.17, add 19.22 to it, then that will give us an estimate of what we think somebody might score on Y. And if we look at the variance to think about homogeneity of variance, essentially what we're looking at to see if this spread that we see here is pretty similar at each level of X. And what we see is it is pretty similar. We see a pretty big range all the way up to 100, a little higher over here. So a little bit more of a restricted range in this low end. But we still have some people up at this high end of evoking jealousy who are still down at this low end. So it doesn't feel, hugely problematic in terms of thinking about homogeneity of variance. Questions about that? I feel like the visual of the scatter plot is a little hard to wrap your head around a bit.
I mean, it looks a little messy, but it all makes sense.
And we can see how that distribution is reflected over here as well. So if we remember that on the evoking jealousy scale, there were a ton of people who were pretty low. So we can see all those people down here who were pretty low on that evoking jealousy scale. And not surprisingly, perhaps a lot of them are also low on the cognitive jealousy scale, but not all of them. We still have some variation of people who are very low on cognitive jealousy, but still pretty high on this evoking jealousy scale. Certainly not as many of them. So when we go to conduct the test then, that essentially confirms what we just saw in the scatter plot and tells us about both the strength and the statistical significance. So this gives us essentially a 2x2 kind of a correlation table here. So 2 of those cells are always going to be empty and 2 of them are going to be the same anytime you're just looking at 2 variables. So these boxes are the same and these are the same. So you just need to pull one of these. And so this is row by column. So we go over here to evoking jealousy and we look at the correlation with that and the cognitive jealousy. And we see that the R is 0.403. This is the degrees of freedom that we use, this 1448. And that tells us that P is less than 0.001. So we do have a statistically significant correlation there, and it gives us the asterisk to let us know that. And then we can interpret that. So we see that the R is 0.403. We reject the null hypothesis because that is statistically significant. And we give our whole spiel about cognitive jealousy scores and evoking jealousy scores. And then we find that there's a significant positive association between evoking jealousy and engaging in jealous behaviors. So the jealous behaviors or jealous sort of thoughts, I guess they're not really behaviors on that scale. That's more of like a jealous thoughts, like suspicions kind of a thing. And so, I didn't change that part of the sentence. That's from last year. But this R squared value is right. So what we see is that as cognitive jealousy scores increase, evoking jealousy scores also increase. And so 16.2% of the variance in evoking jealousy scores can be explained by cognitive jealousy scores. So what do you all think about the strength of that association based on the numbers that we talked about at the very beginning?
I'm sorry, I have a question.
Yeah.
Where does the R squared score coming from?
Yeah, that's a great question. I think I always forget to say that. So the R squared is as exactly as it sounds. So it's taking this 0.403 and squaring it. So 0.403 times 0.403.
Oh.
Yeah. It's like the simplest effect size there is out there.
Oh, okay. Yeah. I was like, I don't see that number anywhere. Okay.
Yeah, no, that's a totally good question. I feel like I always just assume that is interpreted as literally as it sounds, and I think you're right that it's not. So thanks for asking.
Yeah.
And when you do the regression line on the scatter plot, that will also give you the R squared up there, so you can also pull it from there. And so if we think about the strength of those associations, that would be a moderate association. So that's a decent association that we see there. And then we would want to think about, is that important? Does that have practical significance? What does that tell us? And again, it's not causation. I think for some variables, it can be really easy to say, well, of course, this helps us understand why people engage in these kinds of behaviors, trying to make their partners jealous, because it's actually coming from their jealousy, right? They're suspicious, and then whatever is happening for them, that translates into trying to make their partner jealous in return. But we don't know that that's causal, right? So those two things are associated and they move in the same direction. But there may be some other thing happening in the background that's influencing both of those variables. And we can never conclude causation, particularly from a cross-sectional survey.
I have another question.
Yeah.
So the R squared is 0.162. So looking at that as far as like the strength of that, are we looking at so on the previous slide, you said the correlation values range from -1 to +1, right?
Yep.
So 0.162 is between 0.0 and 0.2, right?
So make sure that you're not conflating the R value and the R squared value.
Oh.
Yeah. So if you go back,
Okay.
you pop back up, I think I put it here. Yeah, so the correlation values, I would say 0.4 is moderate, but then we would have to go back to the Cohen's effect size evaluations, which are a little bit different to interpret the R squared. So we can interpret either of those.
Oh. Okay.
Yeah, that's a great question. All right, I'm going to pop over to SPSS unless anybody has any other questions before I pop over. All right, so the correlation that I just ran in class was this evoking jealousy scale with the jealousy scores. And so we come up to analyze as always, and then we can come down to correlate. And for our purposes right now, we're going to do bivariate correlations. So we're just including 2 variables in there. I already have mine in there, but we can paste that and see what that looks like in the syntax. It's pretty simple. We can also reset that, but it's the same sort of method of putting those variables into the box. And there's nothing you have to check. There's nothing under options that we need to get. There's nothing under style that we need to change in any way. So that's pretty much it. You can hit OK or you can hit paste.
This is so simple compared to the rest.
It's what? It's so simple compared to the rest, right?
So simple.
I know. It's kind of nice that this comes after Factorial ANOVA because it's just a little breather after that. So this is the same thing that we looked at on the slide. So this correlation between cognitive jealousy and the evoking jealousy scale. And we can run a bunch of things at once too. So if we want to go over to correlation, and let's say we want to put the emotional jealousy and the behavioral jealousy, and trying to not do one that's one of your research questions. Shar, you're looking at evoking jealousy and sexual esteem, right?
Yes.
Okay, so I'm not going to do that one because that would be a spoiler for you. So we'll put all 3 of the jealousies in there. And now you can see that we have a bigger correlation table. And we can come over here and look at the evoking jealousy score and see its correlation with the cognitive jealousy score, its correlation with the emotion jealousy score, and behavioral jealousy. So it seems to have the strongest associations with cognitive and behavioral jealousy. But less so with emotional jealousy. Still a significant association, just a weaker one there. And we can also look at the other correlations, for example, between each of the dimensions of jealousy. So we can look at cognitive jealousy and its association with emotional jealousy and behavioral jealousy. It makes sense that the more suspicious you are of your partner, the more you engage in jealous kinds of behaviors, like searching their, pockets, whatever. And then these are mostly then redundant because we see the emotion subscale looking at the correlation between cognitive and emotional jealousy, which is the same thing over here. So it's essentially a lot of repetition, but it just gives you all the rows, everything in this row correlated with each of these things in the columns. So you can throw a ton of variables in there. It's just a matter of how much of a pain it is to look at and decipher. Any questions about let's do a scatter plot. So the instructions are in the slides and also in your book as well. But I think the best way to do the scatter plots is to go to graphs and then legacy dialogues, and then come down to scatter or dot and click on that. And you don't have to change anything. It'll be on simple scatter already. So you can just go to define, and then you just decide which goes into which variable, into the y-axis or the x-axis. And you may say, like, I'm really thinking of this in the other way. This one in my head made sense as thinking about evoking jealousy as kind of the outcome, and cognitive jealousy as the predictor. But there are, situations in which you might think of that differently. And you don't really need to do a whole lot here. You don't need to do anything over under the options. You can put a title on it if you want to. You can also do that afterwards. And so that's all you need to do there. And that pops that out. And so as you see, that doesn't have that regression line on there that we looked at before. So then once you get that graph, that scatter plot, you can come in here, and there's this button right here, and you may have to hover over it to get the options to show up, but it just says add fit line at total. And so you add that fit line, and it'll ask you if there's if that's a not linear relationship, do you want to change the way that we create that regression line to not be a linear relationship? For us, we're going to assume linearity. So we're just going to leave it as it is. So that puts that R squared up there for us. That puts that fit line, that regression fit line. And then we can just close it, and everything now is on this graph. If we wanted to go in and put a title on it, there's all sorts of graph options under here where you can change the way different things look. You can change colors, scales, things like that. And then once you do whatever it is you do in Chart Editor, you just close it and it saves all of that. So that's the graph.
I have a question.
Yeah.
I just keep missing it. What are you clicking to get to that box where you put the regression line?
Just double clicking on the graph.
Oh, you just double click on it.
Yep.
Okay.
So once you double click on it, that should open up.
Okay.
Yeah. And then you just hit fit line at total, and that will give you that.
Okay.
And so we could look at the same thing and do a graph with the other kinds of jealousy. And so we could pull cognitive jealousy out of here and look at behavioral jealousy. Same sort of a thing. We see a little bit even more clustering over here down at this lower end. And if we double click on it and do add fit line at total, that gives us that fit line there. And we can just close that and close that. And this gives us our R squared value up here. So 14% of our of the variance in the evoking jealousy scores can be explained by the behavioral jealousy scores. So jealousy begets jealousy, I would say is the take-home message there. And that's probably related to all sorts of other stuff. And so if you were to say, for example, I want to control for the effect of one of the kinds of jealousy. I don't know theoretically why you would necessarily do that, but if you wanted to say, I want to remove the effect of cognitive jealousy, maybe for example, and just look at the association between evoking jealousy and behavioral jealousy. You could do a partial correlation, which will partial out or control for the effect of cognitive jealousy and give you a bit more pure of an association between those. Because as we saw when we looked at all the correlations, we see that behavioral jealousy and cognitive jealousy are pretty highly associated. So you might want to say, I want to pull out that cognitive jealousy and get a more pure sense of just that association. And so we could do that. And in fact, we see that it's still statistically significant, but it's a much smaller association. So before, I think that association was 0.386. And we see that once we partial out cognitive jealousy, we have a smaller association there. So we can always do that as well. Any questions about the SPSS end of things?
No, I mean, that was really easy. Pretty simple.
Right? I know.
Yeah.
Yeah, I always love going to this lecture because I feel like everyone's going to be like, oh, that's it? And then sometimes people are like, I feel like I'm not doing enough. I'm freaking out. And I'm like, no, you're not.
Yes, seems a little too simplistic.
Right? You're like, this is suspicious. Yeah, it is actually pretty simple. We can make it a lot more complicated and get into some of the other kinds of correlations. So I just showed you the partial correlation, where we take that third variable out and essentially hold that constant to get a more pure look at the other two variables. The Spearman's Rho correlation is very similar. It looks very similar. You evaluate it in the same way. But it's particularly good for variables that are not normally distributed. Sometimes count variables can be really good for Spearman's Rho, like number of acts, number of partners, something like that. And this can be used in situations where we have ordinal variables, so like two rankings. Your book gives examples of like grades and amount of study time if we measured that in categories, like 1 to 2 hours, 3 to 5 hours, whatever. Kendall's tau is a very similar sort of a thing. It's a non-parametric correlation analysis. It does the same thing with ordinal or sort of ranked variables. It tends to be a little bit better for smaller sample sizes than the Spearman's Rho does, but very similar things. And there are variations of the Kendall's tau that handles rank ties slightly differently, and that's when if you were saying you have two different ranked variables and you have a whole bunch of people who have the exact same ranking on both of those, it mathematically handles those a little bit differently. So you don't really need to worry a ton about it from your end unless you have a lot of ties in those ranks. And then a point by serial correlation is actually pretty much the same thing as a t-test. So it's when we have one of our variables is continuous and the other one is dichotomous. And we code that as 0 and 1. So that gives us the exact same thing as we would get in a t-test, and you could run either of those. It's really totally up to you. And I think your book might give the formula at some point for how to convert R to T, and vice versa. There are a lot of mathematical similarities in what's happening in the equations behind each of those. And so we can equate them and calculate back and forth from one to the other. So lots of directions we could go in, and that's just sort of scratching the surface. There are folks who do larger levels of correlations, like canonical correlations, where they're looking at a bunch of different variables all at the same time. Correlation and this idea of association also is the backbone for a lot of structural equation modeling. It's certainly the backbone for regression, which we'll talk about more next week. So I feel like once you sort of get the basics of correlation, it opens up a whole lot of other statistics for you to think about. Your book has table 5.4, which gives some of the different kinds of correlations and the situations in which you would use them. And they're all pretty straightforward in SPSS as well. So again, pretty simple, both conceptually and in terms of execution. Any questions about correlation before I jump into talking about the assignment for this week?
Oh, go for it.
Wait, I have one question.
Yeah.
Can you go back, sorry, I'm a little sick, into talking about which number you're looking at for moderate, to say if it's a moderate correlation or if it's a more extreme. It was like way back when, I know, but.
Yeah, like at the very beginning, you mean? When I was
yeah.
showing
I think the part I'm just like, wasn't exact. Yeah, that one.
Yeah.
The correlation value.
Uh-huh.
Where are you seeing that SPSS, that number?
So this number is the R value. And so in the example that we went through in class, it's the 0.403.
Okay, that's what I thought. Okay.
Yeah. So I would say that's a moderate association.
Okay.
Yeah, that's a great question. All right, so let me pop back over to the assignment. So as usual, download the data set and answer the research questions. There are 3 research questions because correlation is easy, so I figured I'd throw 3 at you this time. And there are 3 partly also because we're looking at the association between attachment and partner phubbing. And so there are 3 different attachment styles using the state adult attachment measure. And so we'll look at the association between secure attachment scores and phubbing, avoidant attachment scores and phubbing, and anxious attachment scores and phubbing. That is
Great.
What?
So this is great for my dissertation.
There you go.
Fine, yeah.
Perfect. Yeah, and so same sort of a thing, same kind of write-up as we've been doing. So you can use those same templates. The only difference is that there are 3 questions, but they're all, essentially the same question, just using the different markers of attachment. So that should be fairly straightforward for you. Any questions about the assignment and yeah, you all are done with 8:32, so you're good on class weekends.
So in terms of like the template, I know you're like, well, we have our own template, but in the actual assignment, you have the references. So these are the ones we need to use, not anything additional, correct?
You might want to use something additional to support your hypothesis. Do I have that open? No, but I can open that. I think I just had the references from the 2 measures in there are the ones that I had in there. So you would include those because you'll have the measures section there. But then if you pull in any other literature to support your hypotheses, then you'll include those references as well. Any other questions? I know that feels like so short and easy, right? Kind of.
I'm like, no. I'm not, even, not easy at all.
I'm like, I'll see when I'm looking at SPSS by myself.
Right. Do you all want to run through any more examples, or would that be helpful to you? Or
No, honestly, I feel like it is.
Well, Melvin can speak for himself. I'd like to.
I did.
Only because I felt like I missed. I know I can watch the recording, but yeah, if anybody else has to go, I'm cool. But I am on.
I can run a couple of more. Let me just make sure I don't run anything that is somebody's question. So let's look at something. Melvin, you're looking at attachment and sexual esteem, right? And some people are looking at jealousy and sexual esteem.
Yes.
Rachel, you're looking at phubbing and sexual esteem? Or phubbing and jealousy?
I mean, I don't know what the other Rachel is looking at. I'm not looking.
Right.
Other Rachel, your turn.
Is other Rachel still there? I love that we're all just other Rachel. Maybe other Rachel is gone.
I
think other Rachel left.
Okay. Well, then she's not seeing this. So we're going to put phubbing in there. And what else do we want to put in there?
Attachment style?
Attachment style? No, that's what you... Nice try. That was good. You're like, maybe she's sick and like she's not going to notice that. What are our other variables? And I also forgot I'm not sharing screen with you anymore. Let's look at phubbing, and I might have actually deleted sexual esteem from the correlation data set. So I'm going to pull back up the factorial ANOVA data set because I think I left it in there. Perhaps. I think I did. Who is looking at body appreciation?
Me.
And what you're looking at body appreciation and sexual esteem?
Yes.
Okay, so let's look at body appreciation and jealousy. I don't think anybody's looking at that. So let's do body appreciation and...
Is that in this data set? I'm looking.
No, I switched over to the factorial ANOVA data set because I think I have more variables left in there.
Okay, so I'll just watch.
Share
Okay.
screen with you all again. So I'm going to put all three of the jealousy types and body appreciation, and let's look at attachment. I don't think that gets anybody's questions, right? Correct. Right? I think that should be good. I'm not going to make a spoiler alert for anybody. So if you come over here, this is a whole lot of correlations to look at, and I can go back and do just like one or two. So if we look over here at each of these three jealousy scores in each of these rows, and we can come over here to body appreciation scores. And actually, I will just run each of those one by one because I think it's easier to see.
And that was the question. Like I was trying to like go through. So it doesn't matter if you do it all together or one by one. It's still
same.
Bivariate.
It's still doing bivariate between each of them. Yeah, exactly. So if we wanted to do just like body appreciation and cognitive jealousy, let's say, we could just run those two, and we see that correlation is negative 0.112. So the R is negative 0.112. And so what that tells us is that the association is negative, such that as body appreciation scores increase, cognitive jealousy scores decrease, or you could say it the other way around. And that R value of 0.112 tells us that that's a pretty weak relationship, but it is statistically significant. And if we look up here at body appreciation and cognitive jealousy, that's the same value we get there.
How do we know which one's increasing, which one's decreasing?
So we can talk about it in flipped ways. So if you think about, for example, the scatter plots between each of these. So if we were going to go cognitive jealousy, and let's just put them, kind of randomly wherever. If we wanted to say cognitive jealousy is a predictor of body appreciation, which we could, say that in either direction, right? We could look at it in that direction. We could also flip these such that cognitive jealousy is on the y-axis and body appreciation is on the x-axis. But what that negative association tells us is that as body appreciation increases, cognitive jealousy decreases. We could say it the other way around, that as cognitive jealousy increases, body appreciation scores decrease. So what we know is that they're essentially they're moving in the opposite directions. Does that answer that question? I'm not sure if I said that well.
So no matter what, if it's a negative correlation, they're going opposite ways.
Exactly. Yep.
So one's increasing, the other is decreasing, and vice versa.
Exactly. Yep.
Okay. I don't know why that concept was really difficult just now.
Yeah, I get it. Yeah. And then the reverse for any positive associations. So if we look at body appreciation and each of the attachment measures, We see that body appreciation is positively associated with the scores on the secure attachment subscale. And so the higher your secure attachment, or the more secure your attachment, the higher your body appreciation scores are. And we see the opposite for each of the other attachment subscales. So the more anxiously attached you are, the lower your body appreciation scores. And the more avoidantly attached you are, the lower your body appreciation scores are.
Now, what would, I don't know why this is like confusing. What would happen if both scores are going down?
Then that would be a positive association.
It's still positive, but they're both going down.
Uh-huh. Yeah, if they're moving in the same direction. And we could say the same thing. So like as secure attachment decreases, body appreciation scores decrease.
Okay, I see. Yeah. The negative and positive was confusing, but I understand now. Okay.
Yeah. Yeah, it's a little tricky when you think about both signs and directions, I think. But yeah, so, and that makes total sense, right? From what we know about attachment, that the secure attachment would be positively associated with body appreciation, and the more insecure attachment styles would be negatively associated with body appreciation. So that's interesting, right?
Yep.
Dr. Wells, so with looking at that, we can only say there's a correlation if it has the two like asterisks next to it.
Right, and you're always looking at that p-value. And so you can tell SPSS, don't even put those asterisks on there. When you go to the correlate piece, there's this little thing for flagging significant correlations. So you uncheck that if you wanted to uncheck flag significant correlations. And always what you're going to look at is this significance value there.
Right.
Yeah.
Thank you.
So like the p-value for this one is 0.016. They're all pretty significant on this one. That's like the least significant association I think we have there. So yeah, there's not a ton of examples of seeing anything but 0, 0, 0. But this one is a situation where the p-value is 0.016. Which is, that's an interesting, the emotional jealousy scale, I think, is an interesting one to think about with the attachment styles, right? That's how upset you would get if your partner were cheating. So the more anxiously attached you are, the more upset you would be. Avoidant attachment is, it's significant, but that's a really weak association. So being avoidantly attached is not all that terribly strongly associated with how upset you would be. And the more securely attached you are, the less upset you would be thinking about your partner cheating. So those all make total sense, right? From if we're thinking about attachment styles. Yeah, so that's correlation. Isn't that fun?
The most fun.
Right? Oh my God, you guys are just gonna like stay home all night tonight and run correlations. I know.
I'm running some now. I'm not.
Awesome. Well, if nobody has any other questions, that's it for tonight.
Cool beans.
Good night. Thank you.
Awesome. Have a great night, everybody.
Yeah, I feel better, Dr. Wells.
Thank you.
Get some rest and all that stuff.
Rest.
What is that? I'm a doctor.
Trust me. Awesome.
Good night.
Good night, everybody.